All right, so today's lesson is about doing u-substitution that winds up making us get logarithms in the answer. So we're going to keep looking to get the form in general 1 over u du. Now I might have an extra number in there, but that's the general thing I'm going for. So in light of that, I could say on this one, since x to the third is a higher degree than the x squared top, let me say that u equals the bottom. And that's generally what you're going to be doing on all the problems today. So you can kind of get a feel for how they're going to go pretty quickly. So using our shortcut from yesterday, I can say that du is 3x squared minus 6x, and all of that would be times dx. Well, that does not look like the top of my fraction. So notice on this, I could factor out the number 3. I could factor out x, but that won't help me as much. If I factor out the number 3, I'm going to have x squared minus 2x and then dx. And sorry, it doesn't look like I'm quite focused. I hope that fixes itself there. So guys, look what I've got. On the original problem, I can take the bottom here and replace it with u. Then I can take the x squared minus 2x out to the side and then dx at the end. So my job is still to replace the x squared minus 2x dx, and I see that here. So do you see that if I isolate x squared minus 2x dx, I'll have to do du over 3 or 1/3 du. So then I can take 1/3 outside of the integral sign, which I won't usually write that step, or I'll go ahead and skip this step and go straight to that step. You'll see me do that quite a bit. But that's going to give me 1/3 ln, don't forget your absolute value of u, plus c. So now the only thing that you need to do is say ln of x cubed minus 3x squared plus c. And there is the answer to that problem. Now let's talk about what if you didn't recognize that that's what we needed to do. Some of you might say, let's factor the top into x minus 2 and the bottom into x squared, x minus 3. But then the problem is you get x minus 3 dx, and you've got a little more of an issue, because then even if you said, well, the bottom I could just make x squared minus 3x, then your u is x squared minus 3x, and your du is 2x minus 3 dx. And 2x minus 3 is not a multiple of this x minus 2. So you kind of hit a roadblock. Now there is something you can do with this, which is called partial fraction decomposition, which I would love to be able to show you. And normally I show you a little bit in Calc 1, but this is basically a Calc 2 topic. And so we're not going to spend time on it in online learning, since we have a little bit less time this year and we're moving a little bit slower. So in other words, when you factor out, you get to a stopping point. You kind of get stuck with it. So it turns out that just going with the way it was originally is actually better. All right, so problem number 2. Let's integrate tangent x dx. Now it's interesting that you know the derivative of tangent x is secant squared x, but we've never even talked about the antiderivative. I mean, the derivatives of sine and cosine just give you cosine and negative sine. That doesn't help. The derivatives of secant and cosecant are the ones that give you secant tangent or negative cosecant cotangent. The derivatives of tangent and cotangent are secant squared and negative cosecant squared. So none of them just give us tangent x. So, what could we do? Well, normally in a situation like this, we start out working with trig identities. Well, if I do that, nothing cancels. What if I do what we did on the last problem? Let the bottom equal u. Then the derivative of cosine is negative sine x. Oh, times your dx, don't forget that. So I'm going to write the problem with the cosine of x as u on bottom. And then I'm going to say, well, I've still got sine x dx that I've got to replace. And again, notice that sine x dx, you can call negative du. I could also just have said, let me call it negative du. In a way, that's a little bit cleaner, but that's up to you. So now I've got negative ln of the absolute value of u plus c. The absolute value of u would be cosine x plus c. Okay, so there is that problem. Now, I will tell you, sometimes, most people are going to say, especially sometimes people will just memorize this antiderivative, but some people will say, well, this is cosine x to the negative 1 power, truly to the negative 1 power, not cosine inverse of x. Well, that means 1 over cosine x. So occasionally, some people will memorize this as ln of secant x plus c. And that's not usually the way I think about it, but that's certainly an okay way. Okay, so now let's do a definite integral. And sometimes they're more tricky, especially because you have to be real careful with your numbers and not do something goofy, like say that, what was it, 44 over 80, divide by 4, divide by 5 is 16? No, divide by 4, divide by 4. So obviously that bug can bite all of us. So sometimes the definite integrals are a little more tricky because of that, but let's work on this one. Now, one thing you might want to do is say, okay, I've got 27/8. Maybe I make this 1 over x to the 2/3 and 1 over 1 plus x to the 1/3 dx. And the question is, I'm going to let part of the bottom equal u. Which one? Well, usually it's the bigger one. I could try letting u be the smaller one, but then du would be 2/3 x to the negative 1/3, which would be 2 over 3 x to the 1/3, and don't forget your dx out there. And I'm not really seeing what I would do. Like, I see an x to the 1/3, but I'm just not sure how I'd work that in. So let's go about it the other way. Usually, if you got an option, you want the u to be the 1 plus x to the 1/3, because it's a binomial. It's a little bit more. So you're cleaning up, you're making a little bit bigger the part of the problem u, which makes the bigger part smaller. That's kind of what you're thinking. Now, the derivative of 1 plus x to the 3rd is just 1/3 x to the negative 2/3 dx. I'll be a little bit better this time since I'm going to do this officially. Well, that's 1 over 3 x to the 2/3 dx. Okay, now I'm saying that the x to the 2/3 is a monomial that's in the du part. So, hey, while I'm here, let me replace my limits too. So if this is my u, if I put my high x in there, it would be 1 plus 27 to the 1/3, which is the cube root of 27. The cube root of 27 is 3, plus 1's 4. And when I put my low x, 8, in there, it would be 1 plus 8 to the 1/3, or the cube root of 8. And 2 plus 1's 3, okay? So here's what I'm going to do. I'm going to go ahead and say, well, I'm going from 3 to 4 on my limits. So I'll get those turned over. And let's see here. I've got this part. I'm going to go ahead and call 1 over u. And then I've still got the 1 over x to the 2/3 here and the dx there. Oh, look, in this piece, if I wanted just 1 over x to the 2/3 dx, I could multiply everything by 3. My 3's would cancel and I'd have 3 du. So let's make that 3 to 4, 1 over u, and then 3 du. And you know, oh, excuse me, you know that 3 could be just put here. That tends to make it easier. I've not shown it that way a lot in the homework keys because I'm thinking if I show it the other way, you can follow my homework quick keys better. But if I'm actually doing the problems on my own, I go ahead and say 3 du and split the number to the front and the du letter part to after the integral sign. So now I am almost there. So I know I've got 3 times ln of the absolute value of u, and I'm going to take that 4 to 3. So that's going to give me 3 ln of the absolute value of 4, which is 4, minus ln of the absolute value of 3. The absolute value of 3 is 3. And then you'll see this as ln of 4/3. So don't forget, if you've got 2 separate logarithms and you're subtracting, you condense into a single logarithm by dividing arguments. If this had been plus, you would have said 4 times 3 and have gotten 12. But it's minus, so I'm not going to mess that up. All right, so let's do a crazy one. If I ask you to find the antiderivative of secant x dx, well, we've already seen one kind of like this when we did the antiderivative of tangent x. And we said, oh, we'll use trig identities and make it 1 over cosine x dx. The problem is, when I had sine over cosine, if u was cosine, du could have been negative sine x dx. I don't have a negative sine x dx on the top, so that's not going to work here because if I tried to replace, I would have 1 over u for this part, and then the dx would have to be du over negative sine x, and there's no way to get the x out of the problem. And remember, you can't do anything until you have all u's. You can't work with part u's, part x's. That just doesn't work. So let me tell you, just like we did the antiderivative of tangent x, we would do the antiderivative of cotangent x similarly. Just like we're about to do the antiderivative of secant, you'll do the antiderivative of cosecant similarly. And this is something where you can either memorize process or memorize the antiderivative, and that's up to you which one you prefer to do. This is not something that I would come up with on my own. What we're going to do is we're going to multiply secant x by fancy 1. So I'm going to multiply it by secant x plus tangent x over secant x plus tangent x dx. So I'm multiplying by 1, which is legal because I'm not changing the integrand, so I'm not changing the problem. Why would I do such a thing? Well, let me make it a little more compact. So I've got secant plus tangent on the bottom, and on the top I'm going to distribute and get secant squared plus secant tangent. Okay, now these look like secant squared and secant tangent. Those are derivatives, I know. So we're going to stick with what we're doing today, which is to let the bottom essentially, or at least part of the bottom, be your u. Well, when I do du, what's the derivative of secant? Secant tangent. And what's the derivative of tangent? Secant squared. Don't forget your dx. So guys, do you see how nicely this is wrapping up? That I just replaced the bottom with u, and all of this, the secant squared plus secant x tangent x dx, all of that is your du. Aha. So I've got ln of the absolute value of u plus c, and that's ln of the absolute value of secant x plus tangent x plus c. Oops, I'm off the board, sorry. Hey, just FYI, when you get to this point, if you want to skip this step and do the antiderivative and sub back in your x's, I'm fine with that. That's fine. That's cool. That'll save a step of writing. All right, so we're going to do the next problem. We're going to use this information. All right, so now let's evaluate this definite integral. You might be saying, Ms. Porter, you just told us we were going to use the information we just did. That's right, okay? So here I'm looking at it going, normally I would let u be everything under the radical, but I can already see that's going to get me jammed up because the derivative of this is 2 times tangent x to the first power times the derivative of tangent x, which is secant squared x times dx. What do? That's all kinds of extra garbage. Well, what do you do anytime you have trig and you don't seem to be moving forward? Look for trig identities. So when I look at 1 plus tangent squared, remember we did this yesterday, we said your Pythagorean identities are sine squared plus cosine squared equals 1. If you divide everything by cosine squared, sine squared over cosine squared, try that again, sine squared over cosine squared, cosine squared over cosine squared, 1 over cosine squared. Ha! Tangent squared plus 1 is secant squared. So I'm going to rewrite this problem using identities. So now I'm down to the square root of secant squared x dx. Okay, yeah, you're right. That is just the antiderivative of secant x. So we just did that. Now we can reinvent the wheel. I tend to remember multiply by secant plus tangent. Sometimes I don't remember exactly what the answer is, but we just did this. So I know that the antiderivative of secant is ln of secant plus tangent. And I'm going to go from 0 to pi over 4. So I didn't necessarily do u-substitution this time because I did u-substitution last time. So let's see here. That's going to give us ln. Now, the secant of pi over 4. Now, let's see. In the 45, 45, 90 triangle, the secant of 45 degrees is just square root 2. Plus the tangent of pi over 4. Tangent 45 is 1. Okay, now wait a minute. 1 plus the square root of 2 is positive. So I'm going to go ahead and say it already is positive, so I don't need the absolute value bars to force it to be positive. So I'll just go with parentheses. Minus ln of secant 0. Now remember, on the unit circle, cosine of 0 is 1. So secant is 1 over 1. Tangent 0 is 0. Well, again, 1 plus 0 is 1. So it's already positive. So I've got ln of the square root of 2 plus 1 minus ln of 1. Guys, remember, ln of 1 is just 0. That zeroes out. So I've got ln of the square root of 2 plus 1, and there's my answer. So your last problem of the day, we're going to end on another definite integral. So my final answer is going to be just a number. All right, so I'm going to integrate from pi over 4 to pi over 3 of the fraction 1 over cosine squared theta times 1 plus tangent theta d theta. Now, you don't absolutely have to rewrite the problem, but sometimes it helps people to get less overwhelmed, if you write it like this, okay? That black shows up a little bit better on camera too, doesn't it? So you generally are not going to multiply it out unless you can't do anything else, and multiplying gives you the opportunity to use identities that will help shrink the problem somehow. But in this case, I'm thinking that the u is the binomial. And again, today's topic is to let the bottom or part of the bottom be your u. So du is going to be the derivative of 1's just 0. The derivative of tangent theta is secant squared theta, d theta. Okay, so that's going to let me replace this fraction with 1 over u. And then I've still got 1 over cosine squared theta d theta. Are you seeing what I'm seeing? So is this not the same thing as secant squared theta d theta? That means I can just sub in du. So now I've got 1 over u du. The thing that I'm missing is this is a definite integral. So I've got all u's, which means I need to go not from a low and high theta value, but to a low and high u value. So go up here to your definition of u. If you plug in pi over 3, 1 plus tangent pi over 3 will be your high u value. Tangent of pi over 3 is tangent 60, and from the 30, 60, 90 triangle, that's the square root of 3. So 1 plus square root of 3 goes there. And then when I plug in my low u, it would be 1 plus tangent pi over 4 is my low theta. So tangent of 45 degrees is 1. So this is 1 plus 1 is 2. So that's my lower limit. All right, so now I'm simply going to say that's ln of the absolute value of u. I hope that's no big deal at this point. And I'm going to go from 1 plus the square root of 3 to 2 on the bottom. So that's ln of the absolute value of 1 plus the square root of 3. But 1 plus the square root of 3 is always already positive, so you don't have to hit it again with the absolute value bars. Minus ln of the absolute value of 2. But again, 2 is already positive, so you don't have to add in the absolute value bars. If you had ln of negative 2, once you did absolute value bars, that would change it to ln 2, okay? But you don't have to keep dragging the absolute value bars around with you if it's already positive, or you can simply make it positive. Remember, because we have properties of logarithms, I can condense, and my final answer will be ln of 1 plus the square root of 3 over 2. So don't be weirded out when you get strange answers like this. And guys, that's it for the day. You gave me 6, so hopefully that means you're going to score a touchdown when you get to the homework.